Right now, at this very moment, you're standing on a planet that's spinning at over 1,000 miles per hour. You're orbiting a star at 67,000 miles per hour. And that star is racing through a galaxy at nearly 500,000 miles per hour. You are hurtling through space faster than any rocket we've ever built, and you don't feel a thing. If you're in the heart of Manhattan right now, surrounded by towering skyscrapers reaching toward the heavens, Times Square blazing with 1,000,000 lights, each one a beacon in the urban night. Imagine every single light you see, every glowing window, every street lamp, every car headlight, to multiply that by 100 billion. That's just the beginning of comprehending the Milky Way. Or perhaps you're gazing at the Grand Canyon at sunset, watching layers of ancient rock painted in crimson and gold, carved over millions of years. The canyon stretches 18 miles across, revealing Earth's history in stone. Now picture a canyon so vast it would take light itself, travelling at 671 million miles per hour, 100,000 years to cross from one side to the other. That's the disk of our galaxy. Maybe you're in Texas, standing beneath that legendary big sky, where the horizon seems to stretch forever in every direction. Take that feeling of infinite space, that sense of endless possibility, and multiply it by infinity itself. Because tonight, we're not just looking up at the stars, we're embarking on the most ambitious journey ever conceived. We're going to travel across our entire galaxy, from the nearest stars you could theoretically reach in your lifetime, to the supermassive black hole lurking at the very heart of the Milky Way. We'll visit ocean worlds, where the seas are 100 kilometers deep. We'll witness dying stars in their final, spectacular death throes. We'll explore planets where it rains molten iron, where the ground beneath your feet is made of crystallized carbon, of diamond worlds larger than Jupiter. We'll stand at the edge of black holes, where space and time themselves break down. And we'll discover that our sun, our Earth, our entire solar system, is hurtling through space at 500,000 miles per hour, orbiting a monster we can barely comprehend. This isn't just a documentary. This is a 2-hour odyssey across 200,000 light years of space. Every second of this journey has been crafted with obsessive detail, every fact verified. Whether you're watching this in New York, London, or Tokyo, whether you're a student, a teacher, an engineer, or simply someone who looks up at the night sky and wonders, this journey is for you. So here's what we'd love from you. If you're ready for this adventure, if you want to be part of this community of cosmic explorers, hit that like button. It tells us you're ready. It tells YouTube to share this journey with others who are also searching for something greater. And if you want to join us for every future voyage, every new discovery, every mystery we unravel together, subscribe to Whispering Wonders of Science and turn on notifications. Because this is just the beginning. We're about to leave Earth behind. We're about to travel farther than any human has ever gone. The Milky Way is waiting. Are you ready? Then let's begin. Our first destination lies 4.37 light years away. To put that in perspective, if you could somehow drive your car through space at highway speeds, 70 miles per hour, it would take you over 40 million years to reach it. Light itself, the fastest thing in the universe, takes 4 years and 4 months to make this journey. We're heading to Alpha Centauri, our closest stellar neighbour. But this isn't just one star. It's an entire system, a family of 3 stars locked in an eternal gravitational dance. Massive thermonuclear furnaces, each one a sun in its own right, orbiting each other in a cosmic ballet that's been going on for billions of years. The brightest and most massive is Alpha Centauri A, or as some astronomers call it, Rigil Kentaurus, which means the foot of the centaur in Arabic. This is a beast of a star. With a mass 1.1 times that of the Sun and a diameter 1.22 times larger, Alpha Centauri A is what we call a G-class star, just like our own Sun. But here's where it gets interesting. Even though it's only slightly bigger than the Sun, it pumps out 1.5 times more energy. Its surface temperature reaches 5,790 Kelvin, or 10,422 degrees Fahrenheit. That's about 500 degrees hotter than our Sun. If you were somehow standing on a planet orbiting Alpha Centauri A, protected by some miraculous spacesuit, The star overhead would look similar to our sun, just brighter, more intense. The sky might have a slightly different hue, perhaps a bit more white than yellow. And if you looked carefully, you'd see another bright point of light in the sky, almost as bright as Venus appears from Earth. That would be Alpha Centauri A's companion, Alpha Centauri B. Alpha Centauri B, also called Ptolemy, is the smaller sibling in this stellar family. With a mass of about 0.9 solar masses and a radius of 0.86 times the Sun, this K-class orange dwarf is slightly cooler and dimmer than its partner. Its surface temperature hovers around 5,260 Kelvin, or 9,000 degrees Fahrenheit. That might sound hot, and it is, but in the world of stars, this is actually relatively cool. The cooler temperature gives the star an orange tint, like a cosmic tangerine glowing in the depths of space. These two stars orbit each other in an elaborate cosmic waltz that takes 79.91 years to complete. Sometimes they're as close as 11.2 astronomical units apart. That's roughly the distance from the Sun to Saturn. At their farthest, they separate to 35.6 astronomical units, about the distance from the Sun to Pluto. Imagine watching one of these stars rise in an alien sky, knowing that over the course of decades, it would grow brighter and dimmer, closer and farther, in an endless cycle. But wait, we're not done, because there's a third member of this stellar family, and this one is special. This one is our closest stellar neighbour of all. Meet Proxima Centauri. At just 4.243 light-years away, Proxima is the closest star to our Sun. But don't let that proximity fool you into thinking it's impressive to look at. Proxima is a red dwarf, the most common type of star in the galaxy, and one of the smallest, dimmest stars you can imagine, with a mass of only 0.122 solar masses, or about 12% the mass of the Sun, and a radius 7 times smaller. Proxima is barely larger than Jupiter. In fact, if you put Jupiter and Proxima side by side, you'd have to look carefully to tell which was which, at least in terms of size. The surface temperature of Proxima is a relatively cool 3,000 Kelvin, or about 4,940 degrees Fahrenheit. That might still sound incredibly hot, and it is by human standards, but in the world of stars, this is downright chilly. The cool temperature gives Proxima a deep red colour, like a dying ember in a cosmic fireplace. And here's the kicker. Despite being our closest stellar neighbour, Proxima is so dim that you cannot see it with the naked eye from Earth. Its luminosity is a mere 0.17% that of the Sun. You'd need a telescope to spot it. Proxima orbits the Alpha Centauri AB pair at a distance of about 13,000 astronomical units, or about 0.21 light-years. That's far enough that some astronomers have debated whether Proxima is truly part of the system or just a passing visitor. But the math says it's bound, taking roughly 550,000 years to complete one orbit around its more massive siblings. Currently, Proxima is slowly getting closer to Alpha Centauri A and B, and in about 26,700 years, it will be at its closest approach. Now, here's where this story gets really exciting, because Proxima Centauri isn't alone. It has planets, and not just any planets, potentially habitable ones. The first planet discovered around Proxima was Proxima Centauri b, found in 2016 using a technique called radial velocity. This method detects the tiny wobble in a star's motion caused by the gravitational tug of an orbiting planet. Proxima b orbits its star at a distance of just 0.0485 astronomical units, or about 4.5 million miles. That's about 20 times closer to Proxima than Earth is to the Sun. If Proxima were the Sun, this planet would be well inside Mercury's orbit, roasted to oblivion. But remember, Proxima is a dim red dwarf, not a blazing yellow sun. Despite its close proximity, Proxima b sits right in the habitable zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. The planet completes one orbit every 11.2 days. Its mass is estimated at 1.17 times Earth's mass, making it slightly heavier than our homeworld. With a radius about 1.3 times that of Earth, Proxima b is likely a rocky planet, not a gas giant. The gravity on its surface would be about 1.1 times Earth's gravity. If you weigh 150 pounds on Earth, you'd weigh about 165 pounds on Proxima b. Noticeable, but not crushing. But here's the catch. Being so close to its star, Proxima b is almost certainly tidally locked, just like our moon is to Earth. One side of the planet eternally faces the star, baked in perpetual daylight. The other side faces away, plunged into eternal night. The day side might have temperatures around room temperature, maybe even comfortable by human standards, while the night side could be a frozen wasteland hundreds of degrees below zero. Imagine standing on the Terminator line, the boundary between day and night. Behind you, the star Proxima glows dull red, huge in the sky, never moving. Before you, darkness, broken only by the stars of the Milky Way. Above, if Proxima b has an atmosphere, you might see perpetual twilight, with winds screaming at hundreds of miles per hour as air rushes from the superheated day side to the frozen night side. Could life exist here? Maybe. If the planet has a thick enough atmosphere, it could redistribute heat, making both sides more temperate. Global ocean could also help, carrying warmth from the day side to the night side. But there's another problem. Proxima Centauri is what we call a flare star. It regularly unleashes massive bursts of radiation and charged particles that would strip away a planet's atmosphere over time, sterilizing the surface with lethal ultraviolet light. For life to survive on Proxima b, the planet would need a strong magnetic field to deflect this radiation, and we simply don't know if it has one. In 2020, astronomers confirmed a second planet, Proxima Centauri c. This one is very different. It orbits at about 1.5 astronomical units from the star, well outside the habitable zone. It takes about 1,900 days, or roughly 5.2 years, to complete one orbit. Proxima c is much more massive than Proxima b, with a mass about 7 times that of Earth. This makes it either a large, rocky super-Earth or a small mini-Neptune, a gas dwarf with a thick hydrogen atmosphere. The temperature on Proxima c is estimated at negative 234 degrees Celsius or negative 389 degrees Fahrenheit. That's colder than any place on Earth, colder than the surface of Mars, colder than the moons of Jupiter. This is a frozen world, likely covered in thick ice, with no chance of liquid water on its surface. But here's where it gets interesting. Proxima c might have a ring system, like Saturn. Observations suggest anomalies in the planet's light signature that could be explained by rings of ice and rock orbiting the planet, perhaps 5 times the diameter of Jupiter's rings. Imagine the sight: a frozen ice giant, shrouded in darkness, adorned with glittering rings that catch and reflect the faint red light of its distant sun. And there's potentially a third planet. In 2022, astronomers detected what they believe is Proxima Centauri d, an even smaller world, orbiting incredibly close to the star. This planet, if confirmed, has a mass of only about 0.26 Earth masses, making it one of the lightest exoplanets ever discovered. It orbits at just 0.029 astronomical units, completing a year in only 5.15 days. At that distance, the surface temperature would be around 360 Kelvin, or about 187 degrees Fahrenheit. Hot, but not impossibly so. However, the intense radiation from Proxima would make this world utterly hostile to life as we know it. Now, here's the big question. Could humans ever actually visit the Alpha Centauri system? With current technology, absolutely not. Our fastest spacecraft, the Parker Solar Probe, reaches speeds of about 430,000 miles per hour at its closest approach to the Sun. At that speed, it would still take over 6,700 years to reach Proxima Centauri, the Voyager. Probes, which are currently leaving our solar system, are travelling at about 38,000 miles per hour. At that speed, the journey would take about 75,000 years. But there's hope. Enter Breakthrough Starshot, one of the most ambitious projects ever conceived. The idea is to build thousands of tiny spacecraft, each no bigger than a microchip, equipped with ultra-thin light sails. These nanocrafts would be launched into Earth orbit and then accelerated by a massive array of ground-based lasers. The laser array, spread over 1 square kilometre, would need to generate 100 gigawatts of power. That's roughly equal to the entire electrical output of the United States. But only for about 10 minutes. The lasers would push on the light sails, accelerating the nanocrafts to about 20% the speed of light, or roughly 134 million miles per hour. At that speed, the journey to Alpha Centauri would take just over 20 years. The spacecraft would zip past the system, snapping photos and taking measurements, and then send the data back to Earth, which would take another 4 years to arrive. So from launch to receiving data, we're looking at about 25 to 30 years. It sounds like science fiction, but the physics checks out. The technology is mostly within reach. The biggest challenges are engineering challenges. Building lasers powerful enough, sails thin and durable enough, and electronics tiny and robust enough to survive the journey. But if Breakthrough Starshot succeeds, humans born today could live to see close-up images of another star system. We could see Proxima b with our own cameras. We could potentially detect signs of an atmosphere, maybe even hints of life. For now, though, Alpha Centauri remains a distant dream, but it's a dream that's closer than any other star system. And that's why it captivates us. It's our cosmic next-door neighbour, tantalizingly close, yet impossibly far. As we prepare to leave the Alpha Centauri system, take one last look back. Somewhere in that system, on one of those planets, there might be oceans, there might be weather, there might even be microbial life, clinging to existence in the shadow of a temperamental red dwarf. Or maybe there's nothing but barren rock and ice. Either way, we've taken our first steps into the galaxy. Alpha Centauri is behind us now. Our next destination lies 6 light-years away, and it's one of the strangest stars you'll ever encounter. 6 light-years from the Sun, we find Barnard's star, and this star is in a hurry. Discovered in 1916 by American astronomer Edward Emerson Barnard, this red dwarf holds the record for the fastest proper motion of any star in Earth's sky. Proper motion is the apparent movement of a star across the celestial sphere as seen from Earth, and Barnard's star moves at a blistering 10.4 arcseconds per year. That might not sound like much, but in astronomical terms, it's lightning fast. Over the course of 180 years, Barnard's star moves a distance in the sky equal to the diameter of the full moon. But here's the really cool part. Barnard's star is moving toward us. It's approaching the solar system at about 67 miles per second, or 108 kilometers per second. That's faster than any bullet, faster than any spacecraft we've ever built. In about 9,700 years, around the year 11,800 AD, Barnard's star will be at its closest approach to the Sun, just 3.85 light-years away. At that point, it will briefly become our closest stellar neighbour, surpassing even Proxima Centauri. Barnard's star is old, really old. Astronomers estimate its age at between 10 and 12 billion years, roughly 2 to 3 times the age of the Sun. It's a thick disk star, meaning it's part of an older population of stars that formed early in the Milky Way's history, and being that old, it's had time to slow down. Young red dwarfs spin rapidly, generating powerful magnetic fields that cause violent flares. But Barnard's star is a calm, quiet old-timer. It barely flares at all, or so we thought. On July 17th, 1998, something extraordinary happened. Astronomer Diane Paulson and her team at NASA's Goddard Space Flight Center were analyzing spectral data from Barnard's star when they noticed something unusual, emission lines that indicated a massive flare. At the same moment, William Cochrane at the University of Texas, using the McDonald Observatory, was taking spectra of the star, hoping to find evidence of planets through tiny wobbles in the star's motion. Instead, he caught the flare in the act. The flare was intense. The star's surface temperature, normally a cool 3,100 Kelvin, spiked to at least 8,000 Kelvin in localized regions. That's hotter than the surface of our Sun. For a few minutes, Barnard's star unleashed as much energy as it normally does in weeks. It was like watching a sleeping giant suddenly wake up and roar. This flare proved that even old red dwarfs can surprise us. In terms of physical characteristics, Barnard's star is small. Its mass is about 0.144 solar masses, or roughly 14% the mass of the Sun. Its radius is about 1/5 that of the Sun, making it only slightly larger than Jupiter. The surface temperature is a cool 3,134 Kelvin, and its luminosity is a mere 0.04% that of the Sun. If you replace the Sun with Barnard's star, Earth would be plunged into perpetual twilight, receiving barely enough energy to keep water from freezing. For years, astronomers suspected Barnard's star might have planets. Its high proper motion made it an excellent target for detecting planetary wobbles, and in 2018, those suspicions were confirmed. Using the radial velocity method, astronomers detected Barnard's star B, a super-Earth orbiting the star at a distance of about 0.4 astronomical units. The planet has a mass at least 3.2 times that of Earth, and it completes an orbit every 233 days. But here's the problem. Barnard's star B is not in the habitable zone. The planet receives about 50 times less energy from its star than Earth does from the Sun. Its surface temperature is estimated at about 105 Kelvin, or negative 168 degrees Celsius, negative 270 degrees Fahrenheit. That's colder than Antarctica in winter, colder than the polar ice caps of Mars. Any water on the surface would be frozen solid, locked in ice that's harder than concrete. But wait, there's a twist. What if Barnard's star B has an internal heat source? Tidal forces from the star could flex and squeeze the planet, generating heat in its interior, much like Jupiter's moon Io is heated by tidal forces. Radioactive decay in the planet's core could also generate significant heat. If enough internal heat is present, it's conceivable that beneath the frozen surface, there could be a subsurface ocean, a hidden sea insulated by kilometers of ice. In that dark, pressurized environment, heated by geothermal vents, life could potentially exist. It's a long shot, but it's not impossible. Now, let's jump to our next destination, 8.6 light-years from Earth, and this one you've definitely heard of. This one you can see with your naked eye on a clear winter night. This is Sirius, the dog star, the brightest star in Earth's night sky. Sirius is brilliant. With an apparent magnitude of negative 1.46, it outshines every other star visible from Earth, except the Sun. Only the Moon, Venus, Jupiter, and occasionally Mars are brighter. The name Sirius comes from the Greek word seirios, meaning glowing or scorcher, and it's easy to see why. Sirius blazes with a fierce blue-white light that seems to shimmer and dance in the atmosphere. But Sirius isn't just one star, it's a binary system consisting of two stars orbiting each other. The primary star, Sirius A, is a massive, hot, blue-white main sequence star. With a mass of about 2.06 solar masses and a diameter of 1.71 times the Sun, Sirius A is nearly twice as massive and significantly larger than our Sun. Its surface temperature is approximately 9,940 Kelvin, or 17,632 degrees Fahrenheit, making it much hotter than the Sun's 5,700 Kelvin. Because of this, Sirius A pumps out about 25 times more energy than the Sun. If you were standing on a planet orbiting Sirius A, the star would appear intensely bright, with a harsh blue-white glare. The sky would be bathed in a cold, brilliant light, and any unprotected surface would be scorched by ultraviolet radiation. This is not a gentle, life-giving star like the Sun. This is a fierce, powerful star that dominates its surroundings. But Sirius A has a companion, and this one is even more interesting. Sirius B is a white dwarf, the remnant core of a star that exhausted its fuel and shed its outer layers. White dwarfs are bizarre objects. They pack about the mass of the Sun into a sphere roughly the size of Earth. The density is mind-boggling. A teaspoon of white dwarf material would weigh about 15 tons on Earth. That's the weight of a fully loaded truck compressed into something the size of a sugar cube. Sirius B has a mass of about 0.978 solar masses, nearly the same as the Sun, but its radius is only about 0.0084 solar radii, or roughly 5,863 kilometers. That's just slightly smaller than Earth. Despite its tiny size, Sirius B is incredibly hot, with a surface temperature of about 25,200 Kelvin, or 45,140 degrees Fahrenheit. That's nearly 5 times hotter than the Sun. But because it's so small, its total luminosity is only about 0.026 times that of the Sun. It's a dim, faint ember compared to its blazing companion. The discovery of Sirius B is a fascinating story in itself. In 1844, German astronomer Friedrich Bessel noticed that Sirius A wobbled slightly in its motion across the sky. He hypothesized that an unseen companion star was tugging on Sirius A gravitationally. In 1862, American telescope maker Alvan Graham Clark spotted the companion for the first time, a faint point of light near the blazing Sirius A. It was an incredible feat of observation, like spotting a firefly next to a searchlight. Sirius A and Sirius B orbit each other every 50.09 years. Their orbit is elliptical, with the distance between them varying from about 8.2 astronomical units at their closest to about 31.5 astronomical units at their farthest. Right now, in 2025, they're near their maximum separation, making Sirius B slightly easier to observe with powerful telescopes. No confirmed planets have been found around Sirius, though astronomers have searched extensively. The problem is that any planets that might have existed were likely destroyed when Sirius B went through its red giant phase. About 120 million years ago, Sirius B exhausted its hydrogen fuel and began fusing helium in its core. It swelled up into a red giant, possibly as large as the orbit of Earth around the Sun. Any inner planets would have been swallowed whole. The outer planets might have been stripped of their atmospheres and baked by intense radiation. Eventually, Sirius B shed its outer layers in a planetary nebula, and the core collapsed into the white dwarf we see today. The process would have been spectacular. For a few thousand years, Sirius would have been surrounded by a glowing shell of gas, expanding outward at tens of kilometers per second, lit from within by the dying star. Then the nebula would have dispersed, leaving only the binary system we see today, a brilliant blue-white star and its tiny, hot companion. Looking at Sirius from Earth, it's hard to imagine the violence and drama that unfolded there millions of years ago. It's a reminder that stars are not eternal. They're born, they live, and they die. And in their death, they reshape their surroundings, destroying some worlds and seeding space with the heavy elements that will eventually form new stars and planets. As we leave Sirius behind, it's worth reflecting on what we've seen so far. We've visited 3 star systems, and already we've encountered incredible diversity: red dwarfs and blue-white giants, potentially habitable planets and frozen wastelands, ancient stars and violent flares. And we've only just begun. The Milky Way is vast, and it's filled with wonders beyond imagination. Our next stop takes us deeper into the local stellar neighborhood. We're heading into a region of space where stars are packed more closely together, where encounters between systems are more common, and where the future of the solar system might be written. Within 20 light-years of the Sun, there are approximately 131 known objects. These include stars, brown dwarfs, and even a few mysterious sub-brown dwarfs. Of these, only 22 stars are bright enough to be visible to the naked eye from Earth, meaning they have an apparent magnitude of 6.5 or brighter. The rest are dim red dwarfs, faint brown dwarfs, or distant white dwarfs, invisible without telescopes. Is less than, P is greater than. These objects are organized into about 100 stellar systems. Some are single stars, like Barnard's star. Others are binary systems, like Sirius. A few are triple systems, like Alpha Centauri, and some are even more complex. The diversity is staggering. Among these systems are 103 main sequence stars, which are stars actively fusing hydrogen in their cores. 80 of these are red dwarfs, the most common type of star in the galaxy. 23 are more massive stars, including G-class stars like the Sun and A-class stars like Sirius. There are also 21 brown dwarfs in this region. Brown dwarfs are fascinating objects. They're too massive to be planets, but not massive enough to sustain hydrogen fusion like a true star. They're sometimes called failed stars. With masses between about 13 and 80 Jupiter masses, brown dwarfs fuse deuterium, a heavier isotope of hydrogen, but they never get hot enough to fuse regular hydrogen. They glow faintly in the infrared, slowly cooling over billions of years. One particularly interesting object in our local neighbourhood is WISE 0855-0714, or Y0855 for short. This is a sub-brown dwarf, an object even less massive than a typical brown dwarf. With a mass estimated at only 3 to 10 Jupiter masses, Y0855 is right on the boundary between a brown dwarf and a rogue planet. It's one of the coldest known objects of its kind, with a surface temperature of about 250 Kelvin, or negative 10 degrees Fahrenheit. That's colder than the freezing point of water. This object doesn't orbit a star. It drifts alone through interstellar space, a cosmic orphan. There are also 6 white dwarfs within 20 light-years of the Sun, including Sirius B. White dwarfs are the remnants of stars that have exhausted their fuel. They're incredibly dense and slowly cooling. Over trillions of years, they'll eventually cool down to become black dwarfs, cold, dark cinders that no longer emit any light. But the universe isn't old enough for any black dwarfs to exist yet. Even the oldest white dwarfs still glow faintly. Now, here's where things get really interesting. The stars in our neighbourhood aren't static. They're all moving, orbiting the centre of the Milky Way at different speeds and in different directions. And sometimes their paths cross. In the past, some stars have passed very close to the solar system, and in the future, more will come. About 70,000 years ago, a red dwarf called Schultz's star passed through the outer edge of the Oort cloud, a vast shell of icy comets surrounding the solar system. Schultz's star came within about 0.8 light-years of the Sun, or roughly 50,000 astronomical units. That's incredibly close on a galactic scale. As it passed, its gravity disturbed the orbits of countless comets, sending some of them hurtling toward the inner solar system. It's possible that some of the comets we see today were set on their current paths by Schultz's star's visit. Schultz's star is now about 22 light-years away, moving farther from us. But it left its mark. Astronomers studying the orbits of distant Oort cloud objects have found evidence of perturbations that match the timing and trajectory of Schultz's star's flyby. It's a reminder that the solar system isn't isolated. We're part of a dynamic, ever-changing cosmic environment. Looking to the future, we know of at least 694 stars that will pass within 5.16 light-years of the Sun over the next 15 million years. 26 of those will come within 3.3 light-years, and 7 will come within 2 light-years. These close encounters could potentially disrupt the Oort cloud, sending showers of comets toward the inner solar system. Some of these comets might collide with Earth, causing mass extinctions. Others might simply create spectacular displays in the sky, visible for weeks or months. The most famous future close encounter involves a star called Gliese 710. This orange K-class dwarf is currently about 63 light-years away, but it's heading in our direction. In about 1.29 million years, Gliese 710 will pass within about 10,520 astronomical units of the Sun, or about 0.166 light-years. That's incredibly close. It will be the closest stellar approach we know of in the foreseeable future. Gliese 710 has a mass of about 0.6 solar masses, making it about 60% as massive as the Sun. Its diameter is roughly 60% that of the Sun as well. It's an orange dwarf, cooler and dimmer than the Sun, but still a respectable star. When it passes through the Oort cloud, its gravity will perturb the orbits of billions of comets. Simulations suggest that for the next 2 to 3 million years after the encounter, the inner solar system could experience a significant increase in comet activity. Some estimates suggest we could see as many as 10 comets visible to the naked eye every year, compared to the 1 or 2 we see today. But here's the good news. Gliese 710's passage won't affect the planets. The gravitational influence drops off quickly with distance, and the planets orbit far too close to the Sun to be affected by a star passing through the Oort cloud. Earth's orbit will be completely unaffected. The biggest danger is the increased comet flux. If one of those comets happens to be on a collision course with Earth, we'd need to detect it early and potentially deflect it. But statistically, the odds of a catastrophic impact are low. As we continue our journey through the local neighborhood, we come to realize something profound. Space is not empty. It's filled with stars, planets, brown dwarfs, comets, asteroids, dust, and gas. And all of these objects are in motion, interacting with each other through gravity. The solar system is not a fixed, unchanging place. It's dynamic, evolving, shaped by its environment. Right now, the solar system is moving through a region called the local interstellar cloud, a relatively warm and low-density patch of space. The temperature of the gas in this cloud is about 7,000 Kelvin, but it's so diffuse that there's only about 0.3 atoms per cubic centimeter. For comparison, the best vacuum chambers we can create on Earth still have billions of particles per cubic centimeter. The local interstellar cloud is about 30 light years across, and we've been passing through it for about the last 10,000 years. In another few thousand years, we'll exit it and enter a region called the G cloud, which is even hotter and more diffuse. The local interstellar cloud is part of a larger structure called the local bubble, a cavity in the interstellar medium about 1,000 light years across. The local bubble was formed by a series of supernova explosions that occurred between 10 and 15 million years ago. These explosions blew out a huge region of space, heating the gas to over 1,000,000 Kelvin and creating a low-density bubble. The Sun entered the local bubble about 5 million years ago and will remain inside it for tens of millions of years to come. Interestingly, stars form on the surface of the local bubble, where the expanding hot gas compresses cooler molecular clouds, triggering star formation. There are 7 major star-forming regions around the bubble, including the Scorpius-Centaurus Association and the Orion Complex. These regions are producing dozens of new stars every million years. Some of these stars will eventually migrate away from the bubble, spreading out through the galaxy. Others will remain near the bubble for millions of years, gradually dispersing as their parent clusters break apart. As we leave the local neighborhood behind, it's worth pausing to appreciate just how much we've learned. We've mapped the stars within 20 light years. We've identified potential threats and opportunities. We've seen how the solar system interacts with its environment. And we've glimpsed the future, a future where stars will pass close to us, where comets will rain down, where the sky will change. But now, it's time to venture farther. We've explored the closest stars, but the Milky Way is vast. There are wonders out there that dwarf anything we've seen so far. There are stars so large they could swallow our entire solar system. There are planets where the rain is made of iron, where oceans are hundreds of kilometers deep. There are black holes that devour entire stars. And all of this is waiting for us. Our next destination takes us to the constellation Orion, visible from nearly everywhere on Earth. It's one of the most recognizable patterns in the night sky, and it's home to some of the most spectacular objects in our galaxy. If you've ever looked up at the winter sky and seen 3 bright stars in a row, you've seen Orion's belt. Orion the Hunter is one of the most famous constellations, visible from both the northern and southern hemispheres. It's been recognized by cultures around the world for thousands of years. The ancient Egyptians associated it with Osiris, the god of the afterlife. The ancient Greeks saw the mighty hunter Orion, placed in the sky by Zeus. Indigenous Australian cultures saw a canoe. No matter where you're from, if you look up, you can find Orion. Orion is located about 1,300 to 1,500 light years from Earth, and it's packed with fascinating objects. Let's start with the most famous star in the constellation, Betelgeuse. Betelgeuse is a red supergiant, one of the largest stars visible from Earth. If you replace the Sun with Betelgeuse, its surface would extend beyond the orbit of Mars, possibly even reaching Jupiter. The star's radius is about 764 times that of the Sun, or roughly 5.3 astronomical units. That's enormous. To put it in perspective, if the Sun were the size of a basketball, Betelgeuse would be the size of a large building, maybe 6 or 7 stories tall. But despite its enormous size, Betelgeuse isn't actually that massive. Its mass is estimated at between 10 and 20 solar masses. How can something so big not be that massive? The answer is density. Betelgeuse is incredibly diffuse. Its outer layers are so rarefied that they're essentially a vacuum by Earth standards. If you could somehow stand on the surface of Betelgeuse, you wouldn't feel solid ground beneath your feet. You'd just sink deeper and deeper into progressively denser layers of gas until the pressure and temperature became unbearable. The surface temperature of Betelgeuse is about 3,600 Kelvin, or 6,020 degrees Fahrenheit. That's relatively cool for a star, which is why it glows red. But despite being cool, Betelgeuse is incredibly luminous, pumping out about 100,000 times more energy than the Sun. The reason is simple. It's huge. Even though each square meter of its surface emits less energy than the Sun, it has so much surface area that the total energy output is staggering. Betelgeuse is nearing the end of its life. It's already exhausted the hydrogen in its core and is now fusing heavier elements: helium, carbon, oxygen, neon, and silicon. Each stage of fusion produces less energy and lasts for a shorter time. The final stage, silicon fusion, lasts only a few days. After that, the core will be pure iron, and iron fusion doesn't release energy, it absorbs energy. When the core can no longer support itself against gravity, it will collapse in a fraction of a second, triggering a supernova explosion. When Betelgeuse goes supernova, it will be spectacular. For a few weeks, it will shine as brightly as the full moon, visible even during the day. You could read a book by its light at midnight. The supernova will be visible to the naked eye for months, perhaps even a year or more, before it gradually fades. The explosion will release as much energy in a few seconds as the Sun will emit over its entire 10 billion year lifetime. The shockwave will race outward at tens of thousands of kilometers per second, enriching the interstellar medium with heavy elements: gold, uranium, platinum, all the elements heavier than iron that can only be created in supernovae. But when will this happen? Astronomers don't know for sure. Betelgeuse is what we call a variable star, meaning its brightness changes over time. In late 2019 and early 2020, Betelgeuse dimmed dramatically, reaching its faintest level in over a century. Some speculated that this was a sign the supernova was imminent, but it turned out the dimming was caused by a massive dust cloud ejected from the star's surface, temporarily blocking some of its light. Betelgeuse has since returned to normal brightness. Based on current models, astronomers estimate that Betelgeuse could go supernova any time in the next 100,000 years. That might sound like a long time, but on cosmic timescales, it's tomorrow. Betelgeuse is living on borrowed time, a stellar giant in its final days. Now, let's shift our attention to Orion's belt, the 3 bright stars that form the Hunter's Waste. From east to west, these stars are called Alnitak, Alnilam, and Mintaka. All 3 are massive, hot, blue supergiants, thousands of times brighter than the Sun. Despite appearing close together in the sky, they're actually light years apart. Alnitak is about 815 light years from Earth, Alnilam is about 2,000 light years away, and Mintaka is about 900 light years away. They're not physically associated, they just happen to lie along the same line of sight from our perspective. But the real treasure of Orion isn't the stars themselves, it's what lies below the belt. If you look carefully on a dark, clear night, you can see a fuzzy patch of light hanging from the belt like a sword. That fuzzy patch is the Orion Nebula, also known as Messier 42, or M42, one of the brightest and most studied nebulae in the entire sky. The Orion Nebula is a stellar nursery, a vast cloud of gas and dust, where new stars are being born. It's located about 1,350 light-years from Earth and spans about 30 to 40 light-years across. The nebula is visible to the naked eye, with an apparent magnitude of +4, making it one of the few nebulae you can see without a telescope. Through binoculars or a small telescope, it's stunning. A glowing cloud of greenish light with intricate filaments and dark lanes. The Orion Nebula is about 2 million years old, which is very young in cosmic terms. It's actively forming stars right now. Deep within the nebula, hidden behind thick veils of dust, gravity is pulling gas together into dense clumps. These clumps heat up as they collapse, eventually becoming hot enough to ignite hydrogen fusion. A star is born. At the heart of the Orion Nebula is a cluster of young, hot stars called the trapezium. There are 4 main stars in the trapezium, all of them massive, hot, and incredibly bright. These stars are only about 1 million years old, mere infants compared to the 4.6 billion-year-old Sun. The intense ultraviolet radiation from the trapezium stars ionizes the surrounding gas, causing it to glow. This is what makes the nebula visible. Without the trapezium stars, the Orion Nebula would just be a dark cloud, invisible in optical light. The trapezium stars are so hot and bright that they're slowly destroying the nebula. Their radiation is heating and dispersing the gas, blowing it away into space. In a few million years, the Orion Nebula will be gone, and all that will remain is an open cluster of stars, slowly drifting apart as they orbit the galaxy. But the Orion Nebula has one more surprise. In 2022, the James Webb Space Telescope turned its powerful infrared eyes toward the nebula and made an astonishing discovery: over 540 planetary mass objects. These are objects with masses ranging from about 0.6 Jupiter masses to 13 Jupiter masses. They're too small to be stars, but they're not orbiting any star either. They're just floating free in the nebula. Some of these objects are in pairs, orbiting each other. These are called Jupiter Mass Binary Objects, or JUMBOs. They're incredibly mysterious. How did they form? Were they once part of larger planetary systems that were disrupted? Did they form directly from the collapse of gas clouds, like stars? No one knows for sure. But their existence suggests that planet formation might be far more chaotic and diverse than we thought. The Orion Nebula is a reminder that the galaxy is constantly changing, constantly evolving. Stars are born, they live, and they die. Planets form and are destroyed. The interstellar medium is stirred and enriched by supernovae, compressed by shockwaves, illuminated by young stars. Nothing is static. Everything is in motion. As we leave Orion behind, we carry with us a sense of awe. We've seen the birthplace of stars, the death throes of giants, the chaos of planet formation. We've glimpsed the cycle of stellar life and death that has been repeating for billions of years and will continue for billions more. But now, it's time to venture even deeper into the galaxy. We're going to leave the familiar constellations behind and head toward the galactic center. We're going to explore the structure of the Milky Way itself, from its spiral arms to its massive central bulge. And we're going to confront the monster that lurks at the very heart of our galaxy. The Milky Way is a barred spiral galaxy. If you could somehow travel far above the galactic plane and look down, you'd see a magnificent structure, a bright central bulge surrounded by a thin disk, with graceful spiral arms winding outward from a central bar. The entire structure spans about 200,000 light-years from edge to edge, and it's filled with over 200 billion stars. But we didn't always know this. For most of human history, the true nature of the Milky Way was a mystery. Ancient peoples saw the band of light stretching across the sky and told stories about it. In Greek mythology, it was milk spilled by the goddess Hera. In Hindu mythology, it was the celestial Ganges. But no one knew what it really was. It wasn't until 1610, when Galileo Galilei turned his primitive telescope toward the Milky Way, that we began to understand. Galileo saw that the Milky Band was actually composed of countless faint stars, too dim and too close together to distinguish with the naked eye. This was a revelation. The Milky Way wasn't a cloud or a river. It was stars, billions of them. But even Galileo didn't realize the full scope of it. For centuries, astronomers debated whether the Milky Way was the entire universe or just one of many galaxies. In the early 1920s, this debate came to a head in what's now known as the Great Debate. On one side was Harlow Shapley, who argued that the Milky Way was enormous and that the spiral nebulae we observed were small objects within it. On the other side was Heber Curtis, who argued that the spiral nebulae were island universes, separate galaxies like the Milky Way. The debate was settled by Edwin Hubble in 1923. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble observed a Cepheid variable star in the Andromeda Nebula. Cepheid variables are stars whose brightness oscillates in a predictable pattern, and their period of oscillation is directly related to their intrinsic brightness. By measuring the period, you can calculate the star's true brightness. By comparing that to how bright it appears from Earth, you can calculate its distance. Hubble's measurements showed that the Andromeda Nebula was nearly 1 million light-years away, far outside the Milky Way. This proved that Andromeda was a separate galaxy, an island universe in its own right. Curtis was right. The universe was far larger than anyone had imagined. Today, we know that there are at least 2 trillion galaxies in the observable universe. The Milky Way is just one of them. But it's our galaxy, our home, and understanding its structure is crucial to understanding our place in the cosmos. The Milky Way has several major components. At the center is the galactic bulge, a dense, roughly spherical region packed with old stars. The bulge is about 10,000 light-years in diameter and contains about 10 billion stars. These are primarily population 2 stars, old stars with low metallicity, meaning they contain relatively few elements heavier than helium. Extending from the bulge is the galactic bar, an elongated structure about 13,000 light-years long. The bar is composed of stars orbiting the galactic center in elongated elliptical orbits. The bar rotates as a solid structure, completing one rotation about every 250 million years. The spiral arms of the Milky Way emerge from the ends of the bar, trailing behind as the bar rotates. The Milky Way has 2 major spiral arms, the Scutum Centaurus arm and the Perseus arm. These arms contain the highest densities of young, hot stars and are regions of active star formation. There are also 2 minor arms, the Norma arm and the Carina Sagittarius arm. These minor arms are less prominent and contain fewer bright stars. Our solar system is located in a small spur called the Orion Arm, or sometimes the Orion Spur or local arm. The Orion Arm is about 10,000 light-years long and 3,500 light-years wide, though some estimates suggest it might be longer, perhaps over 20,000 light-years. The Orion Arm connects the Carina Sagittarius Arm to the Perseus Arm, like a bridge between 2 major highways. The Sun is located about 26,000 light-years from the galactic center, roughly halfway out to the edge of the galactic disk. We're also close to the midplane of the disk, only about 60 light-years above it. This position gives us a good view of the galactic plane, which is why we see the Milky Way as a band across the sky. The Sun orbits the galactic center at a speed of about 220 kilometers per second, or about 492,000 miles per hour. At this speed, it takes the Sun about 230 million years to complete one orbit. This is sometimes called a galactic year or a cosmic year. Since the Sun formed 4.6 billion years ago, it has completed about 20 orbits around the galaxy. The last time the Sun was in its current position in the galaxy, dinosaurs were just beginning to diversify on Earth. The next time we complete an orbit, if humanity still exists, we might have spread across the stars, building civilizations on countless worlds. Or we might be extinct, replaced by other species, other intelligences. The galaxy doesn't care. It will continue its stately rotation, indifferent to the fate of any individual species. The galactic disk is not uniform. It's divided into 2 components, the thin disk and the thick disk. The thin disk is about 1,000 to 1,300 light-years thick and contains about 80% of the galaxy's visible mass. It's composed primarily of young population I stars, gas and dust. The thick disk is about 4,000 light-years thick and is composed of older population 2 stars. It's more diffuse and contains less gas and dust. Surrounding the disk is the galactic halo, a roughly spherical region that extends out to about 260,000 light-years from the galactic center. The halo contains globular clusters, ancient collections of hundreds of thousands of stars, as well as individual field stars. These are all old population 2 stars, formed in the early history of the galaxy. The halo also contains a significant amount of dark matter, invisible matter that interacts only through gravity. Dark matter is one of the great mysteries of modern astrophysics. We can't see it directly, but we can detect its gravitational influence. Stars in the outer regions of galaxies orbit faster than they should based on the visible mass alone. The only explanation is that there's a lot of invisible mass out there, providing extra gravitational pull. In the Milky Way, dark matter outweighs normal matter by about 10 to 1. Roughly 90% of the galaxy's mass is dark matter. What is dark matter? We don't know. It doesn't emit, absorb, or reflect light. It doesn't interact with normal matter except through gravity. It could be composed of exotic particles that we haven't yet detected. It could be primordial black holes formed in the early universe. It could be something we haven't even thought of yet. Dark matter is one of the biggest unsolved problems in physics. But despite the mystery, dark matter plays a crucial role in the Milky Way structure. It forms an extended halo that stabilizes the galaxy, preventing the outer stars from flying off into intergalactic space. It also plays a role in galaxy formation. In the early universe, dark matter clumped together under its own gravity, forming the seeds around which normal matter gathered to form galaxies. Without dark matter, galaxies like the Milky Way might never have formed. As we journey through the spiral arms, we're struck by the sheer scale of the Milky Way. If you could travel at the speed of light, it would take you 200,000 years to cross from one edge to the other. At the speed of the fastest spacecraft we've ever built, the Parker Solar Probe, it would take about 570 million years. The Milky Way is incomprehensibly vast, and yet it's just one galaxy among trillions. It's part of a larger structure called the Local Group, a collection of about 80 galaxies bound together by gravity. The Local Group is dominated by two large spiral galaxies, the Milky Way and Andromeda. The rest are smaller dwarf galaxies, many of which are satellites of the Milky Way or Andromeda. The Local Group is part of an even larger structure called the Virgo supercluster, which contains about 100 galaxy groups and clusters. And the Virgo supercluster is part of the Laniakea supercluster, a massive structure spanning 520 million light-years. The hierarchy just keeps going, layer upon layer, structure upon structure, all the way up to the cosmic web, the largest known structure in the universe. But we're getting ahead of ourselves. Before we can explore the larger universe, we need to confront the monster at the center of our own galaxy. We need to journey to the heart of the Milky Way and face the supermassive black hole that rules over billions of stars. At the very center of the Milky Way, hidden behind vast clouds of gas and dust, lies Sagittarius A star, or Skr A star for short. This is not a star in the traditional sense. It's a supermassive black hole, a gravitational monster with a mass of about 4.3 million times the mass of the Sun, all compressed into a region smaller than the orbit of Mercury. Black holes are among the most extreme objects in the universe. They're regions of space-time where gravity is so strong that nothing, not even light, can escape. The boundary of a black hole is called the event horizon, and once something crosses that boundary, it's gone forever, unable to send any signal back to the outside universe. For decades, astronomers suspected that Sagittarius A star was a black hole, but they couldn't prove it. The center of the galaxy is obscured by thick clouds of dust that block visible light. But in other wavelengths, particularly radio waves and X-rays, the region is incredibly bright. Astronomers realized that the energy was coming from a compact source, something incredibly dense and powerful. The proof came from observing the orbits of stars near the galactic center. Over the course of decades, astronomers tracked individual stars as they orbited an invisible object. One star, designated S2, completes an orbit around Sagittarius A star in just 16 years. At its closest approach, S2 comes within about 17 light-hours of the black hole, or about 120 astronomical units. It's travelling at over 5,000 kilometers per second, or about 1.7% the speed of light. By measuring the orbits of S2 and other stars, astronomers could calculate mass of the object they were orbiting. The answer was clear: 4.3 million solar masses, all concentrated in a region less than 44 million kilometers across. There's only one object that could be that dense: a supermassive black hole. In April 2022, the Event Horizon Telescope collaboration released the first image of Sagittarius A star. The image shows a dark circular region, the shadow of the black hole, surrounded by a bright ring of glowing gas. The ring is the accretion disk, a swirling vortex of superheated material spiraling into the black hole. The gas in the accretion disk is heated to millions of degrees by friction and compression, causing it to emit X-rays and radio waves. The shadow of the black hole is about 52 millionths of an arcsecond across as seen from Earth. To put that in perspective, that's like trying to see a donut on the surface of the moon. The fact that we can image something that small, that far away, is a testament to the power of modern astronomy. Sagittarius A star is not just sitting still, it's spinning, and it's spinning fast. Measurements suggest that its spin parameter is between 0.84 and 0.96, where 1.0 is the maximum possible spin for a black hole. At this spin rate, the black hole is rotating at a significant fraction of the speed of light. The spinning black hole drags space-time itself around with it, creating a region called the ergosphere, where everything is forced to rotate in the same direction as the black hole. This effect is called frame dragging, and it's a prediction of Einstein's general theory of relativity. The extreme spin of Sagittarius A star has profound effects on its surroundings. It creates powerful jets of plasma that shoot out perpendicular to the accretion disk, carrying energy and matter far from the black hole. It also affects the paths of light and matter near the event horizon, creating bizarre visual effects. Light that passes close to a spinning black hole can be bent into complex patterns, forming multiple images and light rings. Is less than, P is greater than. But despite its fearsome reputation, Sagittarius A star is currently relatively quiet. It's not actively feeding on large amounts of material. Occasionally, it flares up when a clump of gas falls in, releasing a burst of X-rays, but most of the time it's dormant. This is actually surprising. Many other galaxies have supermassive black holes that are actively feeding, surrounded by brilliant accretion disks that outshine entire galaxies. These are called active galactic nuclei, or AGN. The Milky Way's black hole, by contrast, is almost starving. This wasn't always the case. Billions of years ago, Sagittarius A star was likely much more active. It may have gone through periods of intense feeding, when it accreted massive amounts of gas and dust, shining as brightly as a quasar. But today, it's in a quiet phase, waiting for its next meal. The region around Sagittarius A star is one of the most extreme environments in the galaxy. Within a few light years of the black hole, there are thousands of stars, packed together more densely than anywhere else in the Milky Way. Some of these stars orbit the black hole at incredible speeds. S62, one of the closest known stars, comes within about 120 astronomical units of the black hole, or about 4 times the distance from the Sun to Neptune. At its closest approach, it's travelling at about 8% the speed of light. The gravitational forces near the black hole are so strong that they warp space-time, causing effects that can't be explained by Newtonian physics. Time itself flows differently near a black hole. If you could somehow survive near the event horizon, time would pass more slowly for you than for someone far away. This is called gravitational time, dilation, and it's a real, measurable effect. But could Sagittarius A star be something other than a black hole? Some scientists have speculated that it might be a massive concentration of dark matter particles, called a dark matter fermion ball. In this scenario, the dark matter would be so densely packed that it would mimic many of the properties of a black hole, including a strong gravitational field and the ability to trap light. The idea gained some attention in 2014 when a gas cloud called G2 passed very close to Sagittarius A star. Astronomers expected the black hole to tear the cloud apart and devour it, producing a brilliant flare, but nothing happened. G2 passed by relatively unscathed. Some took this as evidence that Sagittarius A star might not be a black hole after all. However, further analysis revealed that G2 was not just a gas cloud. It likely contained a compact core, possibly a young star shrouded in gas and dust. This core provided enough self-gravity to hold the cloud together as it passed the black hole. The lack of a flare doesn't disprove the black hole hypothesis. It just means G2 was more resilient than expected. The dark matter hypothesis also has problems. Dark matter doesn't interact with light, so it shouldn't produce the X-ray and radio emissions we observe. and the orbits of stars near Sagittarius A star are exactly what we'd expect from a black hole. The evidence overwhelmingly points to Sagittarius A star being a supermassive black hole, not a dark matter object. As we contemplate the black hole at the center of the Milky Way, it's humbling to realize that this monster, as terrifying as it is responsible for the galaxy's existence. Supermassive black holes play a crucial role in galaxy formation and evolution. They regulate star formation by heating and expelling gas. They anchor the central regions of galaxies, providing gravitational stability, and they may have been the seeds around which the first galaxies formed in the early universe. Sagittarius A star is not our enemy. It's the engine that drives the Milky Way, the anchor around which billions of stars orbit, and as long as we stay far away from it, we have nothing to fear. At 26,000 light-years away, we're safe. Even if Sagittarius A star suddenly became active and started devouring everything around it, we'd be fine. The black hole's influence drops off quickly with distance, and we're far outside its reach. But we're not done exploring black holes. There are many others scattered throughout the Milky Way, from stellar mass black holes formed from the collapse of massive stars to intermediate mass black holes lurking in dense star clusters. Some of these black holes are actively feeding, surrounded by bright accretion disks. Others are silent, invisible, detectable only by their gravitational influence on nearby stars. Let's visit one of the closest stellar mass black holes to Earth and see what makes it so fascinating. 3,300 light-years from Earth, in the constellation Monoceros, lies a binary star system designated A0620-00, or V616, Monocerotis. At first glance, it looks like an ordinary system, an orange K-class dwarf orbiting an invisible companion. But that invisible companion is anything but ordinary. It's a stellar mass black hole with a mass of about 6.6 times the Sun. The orange dwarf completes an orbit around the black hole every 7.75 hours. That's right, hours, not days or years. The two objects are incredibly close, orbiting a common center of mass in a frenzied dance. The black hole's gravity distorts the star, stretching it into an egg shape. Material from the star's outer layers is slowly being pulled away, spiraling into the black hole in a bright accretion disk. As the material falls toward the black hole, it heats up to millions of degrees, emitting intense X-rays. This is how astronomers detected the black hole in the first place. They observed X-ray flares coming from the system and realized that only a compact object, either a neutron star or a black hole, could produce such extreme temperatures. By measuring the orbit of the orange dwarf, astronomers calculated the mass of the invisible companion. At 6.6 solar masses, it's too heavy to be a neutron star. Neutron stars have a maximum mass of about 2 to 3 solar masses. Anything heavier collapses into a black hole, so V616 Monocerotis must contain a black hole. This system gives us a glimpse of what will eventually happen to the orange dwarf. As the black hole continues to siphon off material, the star will slowly shrink, losing mass over millions of years. Eventually, it will be reduced to a dim brown dwarf, or even a planetary mass object, a former star stripped down to its core. The black hole, meanwhile, will grow slightly more massive, though the amount of mass it gains from the star is small compared to its total mass. Stellar mass black holes like this one are formed when massive stars, at least 18 to 20 times the mass of the Sun, reach the end of their lives. After exhausting their nuclear fuel, the core collapses in a supernova explosion. If the core is massive enough, nothing can stop the collapse. The core is compressed into a point of infinite density called a singularity, surrounded by an event horizon. Astronomers estimate that there are about 100 million stellar mass black holes in the Milky Way. Most of them are invisible, drifting silently through interstellar space, detectable only if they happen to pass near another star or if they're part of a binary system. Finding these black holes is one of the great challenges of modern astronomy. But black holes aren't the only extreme objects in the galaxy. There are planets out there that push the boundaries of what we think is possible. Worlds where the surface is hotter than some stars. Worlds where it rains molten iron. Worlds that have survived the death of their parent star. Let's visit a few of these extreme worlds. Our first stop is K 2-141b, a planet orbiting an orange dwarf 202 light-years from Earth. This planet is tidally locked, with one side eternally facing its star and the other side facing away. The day side is hellish. The surface temperature reaches 3,270 Kelvin, or about 3,000 degrees Celsius, 5,400 degrees Fahrenheit. That's hot enough to vaporize rock and metal. The planet's day side is thought to be covered in an ocean of molten lava, glowing red hot and constantly boiling. Above the lava ocean, atmosphere is filled with vaporized silicates and metals. Imagine clouds made of rock vapor raining drops of molten stone. The winds on K, 2-141b, are estimated to reach speeds of 1.75 kilometers per second, or about 6,300 kilometers per hour. That's 5 times the speed of sound on Earth. These supersonic winds carry vaporized material from the day side to the night side, where it cools and condenses, falling as rain. But this isn't water rain. It's rain made of liquid rock and metal, falling onto a surface that's frozen solid. The night side of K 2-141b is estimated to be hundreds of degrees colder than the day side, possibly even below freezing. The rain solidifies on impact, forming rivers and lakes of frozen lava that slowly flow back toward the day side, where the cycle begins again. It's a planet-wide circulation system, but instead of water, it's rock. Instead of oceans, it's lava. K2-141b is a world of fire and ice, locked in an eternal struggle between heat and cold. But K2-141b isn't even the hottest exoplanet we know of. That honor goes to Kelt-9b, located 670 light-years from Earth. This is a hot Jupiter, a gas giant orbiting incredibly close to its parent star. The star, Kelt-9, is a massive A-class star with a surface temperature of about 10,170 Kelvin. The planet orbits at just 0.0341 astronomical units, completing an orbit every 1.48 days. The surface temperature of Kelt-9b is estimated at 4,600 Kelvin, or about 4,330 degrees Celsius, 7,800 degrees Fahrenheit. That's hotter than the surface of most red dwarf stars. At these temperatures, molecules break apart into individual atoms. The atmosphere contains ionized iron and titanium, glowing with a blue-white light. The planet is slowly evaporating. The intense heat and stellar wind from Kelt-9 are stripping away the planet's atmosphere at a rate of about 10,000 tons per second. In a few billion years, Kelt-9b might be completely stripped down to its core, transformed from a gas giant into a rocky planet. But wait, there's more. Let's visit a planet that survived the death of its star. 4,570 light-years away, orbiting a white dwarf designated V391 Pegasi, is a gas giant called V391 Pegasi b. This planet is remarkable because it shouldn't exist. When V391 Pegasi was a main sequence star, it eventually exhausted its hydrogen fuel and expanded into a red giant. The outer layers of the star swelled up, possibly engulfing the inner planets. But V391 Pegasi b, which orbits at 1.7 astronomical units, was far enough away to survive, though it likely passed through the outer envelope of the red giant star for a period of time. The planet's atmosphere would have been blasted by intense heat and radiation, stripped away layer by layer, but the planet's core held together. Eventually, the red giant shed its outer layers in a planetary nebula, and the core collapsed into the white dwarf we see today. V391 Pegasi b survived, scarred but intact, orbiting the remnant of its former star. This gives us hope for the future of the solar system. In about 5 billion years, the Sun will expand into a red giant, engulfing Mercury, Venus, and possibly Earth. But the outer planets, Jupiter, Saturn, Uranus, and Neptune, should survive. They'll be battered and baked, but they'll endure. And when the Sun finally sheds its outer layers and becomes a white dwarf, those planets will still be there, orbiting a dim, dying ember. Now, let's visit an ocean world, a planet completely covered in water. Gliese 1214b, located 42 light-years from Earth, is a super-Earth with a mass about 6.5 times that of Earth and a radius about 2.6 times larger. The planet's average density is only 1,870 kilograms per cubic meter, which suggests it's composed of about 75% water and 25% rock. If Gliese 1214b really is an ocean world, the water layer could be over 100 kilometers deep. At those depths, the pressure would be immense, about 20,000 atmospheres. Under such pressure, water doesn't behave like the water we're familiar with. It forms exotic varieties of ice that remain solid even at high temperatures. These high-pressure ices, designated Ice 7 and Ice X, are denser than liquid water, so they sink to the bottom of the ocean and form a thick cryosphere surrounding the planet's rocky core. Above the cryosphere is a vast ocean of liquid water, heated from below by geothermal energy and from above by the planet's star. The planet orbits very close to its red dwarf host, at just 0.0142 astronomical units, completing an orbit every 1.58 days. Because of this proximity, the planet is tidally locked. The surface temperature is estimated at about 393 to 553 Kelvin, or 120 to 280 degrees Celsius. At these temperatures, the ocean is in a constant state of boiling. The entire planet is shrouded in thick clouds of water vapor, and the boundary between the ocean and the atmosphere is blurred. Near the surface, the density of water vapor is almost the same as the density of boiling water. It's a steam world, a planet where liquid and gas are almost indistinguishable. Could life exist on Gliese 1214b? Probably not. The high temperatures and constant boiling would make it difficult for complex molecules to form, and the planet's red dwarf host is a flare star, regularly unleashing bursts of radiation that would sterilize the surface. But it's an intriguing world nonetheless, a reminder that planets come in far more varieties than we ever imagined. As we journey through these extreme worlds, it's clear that the universe is stranger and more diverse than we ever thought possible. Every planet we discover challenges our assumptions, forces us to rethink our models, expands our understanding of what's possible, and there are billions more planets out there waiting to be discovered. Who knows what we'll find? 650 light-years from Earth, in the constellation Leo, lies CW Leonis, also known as IRC plus 10216. This is a red giant star in its final years of life, and it's one of the most luminous stars in the Milky Way. At its peak, CW Leonis shines with a brightness of about 11,300 times the Sun, but its luminosity varies dramatically, pulsating over a period of about 649 days. At its dimmest, it's still over 6,000 times brighter than the Sun. CW Leonis is enormous. Its radius is about 560 times that of the Sun, or roughly 2.6 astronomical units. If you placed it at the center of the solar system, its surface would extend beyond the orbit of Mars, possibly even reaching the inner edge of the asteroid belt. Despite its size, its mass is estimated at only 1.5 to 4 times the Sun's mass. This means the star's outer layers are incredibly diffuse, with a density lower than the best vacuum we can create in a laboratory. The surface temperature of CW Leonis is about 2,300 Kelvin, or roughly 2,000 degrees Celsius. That's cool for a star, which is why it glows red. But despite its relatively low temperature, the sheer size of the star makes it incredibly luminous. CW Leonis is what's called an asymptotic giant branch star, or AGB star. These are stars that have exhausted the hydrogen in their cores and are now fusing helium and heavier elements in shells around the core. The process is unstable, leading to dramatic pulsations and mass loss. CW Leonis is losing mass at an incredible rate, shedding about 4 times 10 to the 22nd kilograms per year. That's roughly the mass of Pluto every 10,000 years. This expelled material forms a vast circumstellar envelope around the star, a cloud of gas and dust stretching out to about 84,000 astronomical units, or about 1.3 light-years. The envelope has a mass of about 1.5 solar masses and is about 69,000 years old. It's filled with complex molecules, carbon dioxide, water vapor, ammonia, methanol, and many others. Spectral analysis has identified about 70 different chemical compounds in the envelope. Interestingly, CW Leonis also contains a significant amount of water vapor in its outer atmosphere, which was unexpected. According to standard models of stellar evolution, all the oxygen in a carbon-rich star like CW Leonis should be bound up in carbon monoxide, leaving none available to form water, but observations show otherwise. One hypothesis is that the water forms when ultraviolet radiation breaks apart silicon oxide and carbon molecules in the star's outer layers, releasing oxygen that then combines with hydrogen. CW Leonis will not live much longer. In 10,000 to 30,000 years, it will exhaust its remaining fuel and shed its outer layers in a final spectacular outburst. For a brief moment, the star will shine thousands of times brighter as the ejected material is ionized by ultraviolet radiation from the hot core. This will form a planetary nebula, a glowing shell of gas expanding into space. The core of CW Leonis will collapse into a white dwarf, a dense, Earth-sized object with a mass of about 0.8 solar masses and a temperature of several million degrees. Over billions of years, the white dwarf will slowly cool, eventually becoming a black dwarf, a cold, dark cinder that no longer emits light. But the universe isn't old enough for any black dwarfs to exist yet. Even the oldest white dwarfs are still glowing faintly. The death of CW Leonis will enrich the interstellar medium with heavy elements. The carbon, oxygen, nitrogen, and other elements forged in the star's interior will be scattered into space, eventually becoming part of new stars and planets. This is the cycle of stellar life and death that has been repeating for billions of years. Stars are born from clouds of gas and dust, enriched by previous generations of stars. They live their lives, fusing lighter elements into heavier ones. And when they die, they return those elements to space, where they can form new stars and planets. We are made of star stuff. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all of it was forged in the cores of stars and scattered into space when those stars died. We are, quite literally, the children of dead stars. As we continue our journey through the Milky Way, we encounter more dying stars. Some are white dwarfs, slowly cooling remnants of sun-like stars. Others are neutron stars, ultra-dense objects formed in supernova explosions. A few are black holes, the ultimate endpoint of the most massive stars. Each represents a different pathway in stellar evolution, a different fate for stars of different masses. The Milky Way is constantly changing. New stars are born in nebulae like Orion. Old stars die in spectacular supernovae or quiet planetary nebulae. The interstellar medium is stirred and enriched, compressed and heated. The galaxy is a living, breathing organism, constantly evolving. And in about 4 to 5 billion years, the Milky Way will undergo the most dramatic transformation of all. It will collide with the Andromeda Galaxy. Right now, at this very moment, the Andromeda Galaxy is hurtling toward us at a speed of about 110 kilometers per second, or about 246,000 miles per hour. Andromeda, also known as Messier 31 or M31, is the nearest large spiral galaxy to the Milky Way, located about 2.5 million light-years away. It's visible to the naked eye from Earth as a faint, fuzzy patch in the constellation Andromeda. Andromeda is slightly larger than the Milky Way, with a diameter of about 220,000 light-years and a mass of about 1 trillion solar masses. It contains roughly 1 trillion stars, compared to the Milky Way's 200 to 400 billion. Like the Milky Way, Andromeda is a barred spiral galaxy with a supermassive black hole at its center, though Andromeda's black hole is much more massive, weighing in at about 100 million solar masses. For most of cosmic history, the Milky Way and Andromeda have been orbiting a common center of mass, part of the local group of galaxies. But unlike other galaxy groups, which are being pulled apart by the expansion of the universe, the Milky Way and Andromeda are bound together by gravity. They're falling toward each other, and in about 4.5 billion years they will collide. The collision will not be instantaneous. It will unfold over billions of years, in slow motion by cosmic standards. The first pass will occur in about 4 billion years. At that point, The two galaxies will plow through each other, their disks interpenetrating. Gravity will distort both galaxies, pulling out long tidal tails of stars, gas. The night sky, viewed from Earth, will be transformed. Andromeda will loom huge, filling half the sky, its spiral arms stretched and warped by tidal forces. But here's the surprising part. Despite the collision, individual stars will almost never collide with each other. Galaxies are mostly empty space. The average distance between stars in the Milky Way is about 4 light-years. Even during the collision, when the two galaxies interpenetrate, the odds of two stars actually hitting each other are astronomically small. It would be like throwing 2 handfuls of sand at each other and expecting individual grains to collide. That said, the gravitational chaos of the collision will dramatically alter the orbits of billions of stars. Some will be flung out of the merging galaxies entirely, becoming intergalactic wanderers. Others will be pulled toward the center, where the gas and dust will be compressed, triggering a burst of star formation. The collision will create massive starburst regions, where thousands of new stars are born every year. After the first pass, the two galaxies will separate, moving apart before falling back together. The second pass will occur about 600 million years later. This time, the collision will be more violent, with even more tidal distortion. The galaxies will merge more deeply, their central bulges beginning to interact. The two supermassive black holes, one from each galaxy, will begin a long, slow spiral toward each other. Over the next few billion years, the galaxies will continue to merge, their disks shredded and dispersed, their spiral arms destroyed. Eventually, about 7 billion years from now, the merger will be complete. The Milky Way and Andromeda will no longer exist as separate galaxies. In their place will be a single, massive elliptical galaxy, sometimes called Milkomeda or Milkdromeda by astronomers. An elliptical galaxy has no disk, no spiral arms. It's a smooth, football-shaped collection of stars, with orbits oriented randomly in all directions. Most of the gas and dust will have been used up in the starburst triggered by the collision, so there will be little new star formation. Milkomeda will be a quiet, aging galaxy filled with old, red stars. At the center of Milkomeda, the two supermassive black holes will eventually collide and merge, creating a single, even more massive black hole with a mass of about 110 million solar masses. The merger will release an enormous amount of energy in the form of gravitational waves, ripples in space-time that will propagate outward at the speed of light. What about Earth? Will we survive the collision? The answer is complicated. First, in about 1 billion years, the Sun will have brightened enough that Earth's oceans will begin to evaporate, triggering a runaway greenhouse effect. The surface temperature will rise to over 100 degrees Celsius, making the planet uninhabitable for most forms of life. By the time of the Andromeda collision, Earth will already be a dead world. But even if Earth were still habitable, the collision itself wouldn't necessarily destroy it. As mentioned, stars very rarely collide. The solar system would likely be flung into a different orbit, perhaps farther from the galactic center, perhaps closer. The night sky would change dramatically, with new constellations and far more stars visible, but the sun would continue to shine, and the planets would continue to orbit. The bigger threat comes later. In about 5 billion years, the sun will exhaust its hydrogen fuel and begin to expand into a red giant. Its outer layers will swell up, possibly engulfing Mercury, Venus, and Earth. The inner solar system will be destroyed. The outer planets, Jupiter, Saturn, Uranus, and Neptune, will survive, but they'll be baked by the intense heat from the red giant, Sun. Eventually, the Sun will shed its outer layers and become a white dwarf. The remaining planets will orbit this dim, dying star for billions of years, slowly cooling in the darkness. That's the ultimate fate of the solar system, but perhaps humanity will not be around to witness it. In 4 billion years, we might have spread across the galaxy, colonizing thousands of worlds. We might have developed technologies that allow us to move entire planets, steering Earth to a safer orbit. We might have left the Milky Way entirely, traveling to other galaxies. Or we might be extinct, replaced by other species, other intelligences. The galaxy doesn't care. It will continue its evolution, indifferent to the fate of any individual species. Stars will be born and die, planets will form and be destroyed, black holes will merge, and the universe will expand, carrying galaxies farther and farther apart, until eventually, trillions of years from now, the last stars will burn out and the universe will fade into darkness. But that's a story for another time. For now, the Milky Way is alive, vibrant, filled with stars and worlds beyond counting, and we are here, right now, to witness it. We've travelled far today. We've journeyed from the closest stars, just a few light years away, to the very heart of the galaxy, 26,000 light years distant. We've visited ocean worlds and lava worlds, planets where it rains iron and planets that orbit dead stars. We've seen stars in their infancy, glowing in the stellar nursery of the Orion Nebula, and stars in their death throes, pulsating red giants, shedding their outer layers. We've confronted the supermassive black hole at the centre of the Milky Way and glimpsed the future collision with Andromeda. And through it all, we've been reminded of one fundamental truth. We are cosmically insignificant, and yet we are part of something grand. Think about it. The Milky Way contains over 200 billion stars. There are at least 2 trillion galaxies in the observable universe. That's more stars in the universe than grains of sand on all the beaches on Earth. And yet, here we are, on this tiny blue dot, orbiting an unremarkable yellow star in a quiet corner of the galaxy, capable of understanding all of this. We are made of atoms, forged in the cores of ancient stars. We are animated stardust, organized in such a way that we can look back at the stars that made us and understand our origins. We can map the galaxy, measure the distances to other stars, calculate the mass of black holes, predict the future collision with Andromeda. We can do all of this, not because we're the center of the universe, but because we have curiosity, intelligence, and a desire to understand. Whether you're watching this from New York or New Delhi, from Tokyo or Toronto, from Lagos or Los Angeles, you are part of this cosmic story. Every atom in your body was created in a star. The oxygen you breathe, the carbon in your DNA, the calcium in your bones, it all came from stellar nucleosynthesis, the process by which stars fuse lighter elements into heavier ones. When you look up at the night sky, you're not just seeing distant points of light, you're seeing your ancestors, the stars that died so that you could exist. You're seeing your future, the fate that awaits our sun and every other star in the galaxy. You're seeing a universe that is vast, ancient, and utterly indifferent to us, yet a universe that we can explore, understand, and appreciate. The Milky Way is our home, but it's not our final destination. Humanity has always been driven by curiosity, by the desire to explore, to push boundaries, to see what lies beyond the horizon. We've explored every continent on Earth. We've sent spacecraft to every planet in the solar system. We've landed on the moon and sent rovers to Mars. And now, we're beginning to look beyond, to the stars themselves. Projects like Breakthrough Starshot are just the beginning. Within this century, we might send probes to Alpha Centauri. Within a few centuries, if we develop advanced propulsion technologies, we might send humans. And who knows, maybe in 1,000 years, maybe in 10,000, humanity will have spread across the galaxy, colonizing worlds, building civilizations, continuing the story that began in Africa hundreds of thousands of years ago. Or maybe not. Maybe we'll destroy ourselves before we get that far. Maybe we'll never leave the solar system. Maybe the galaxy will remain forever beyond our reach. But even if that's the case, even if we never travel to the stars physically, we can travel there in our minds. We can map them, study them, understand them. We can look at the universe and know, truly know, our place within it. So the next time you're outside on a clear night, away from the city lights, look up, find the Milky Way, that faint band of light stretching across the sky. Remember that every point of light you see is a sun, possibly with planets, possibly with life. Remember that you're looking at your galactic home, a structure so vast that light takes 100,000 years to cross it, yet so intimate that every star you see is part of your cosmic neighborhood. Remember that the atoms in your hand were once inside a star. Remember that the iron in your blood was forged in a supernova. Remember that you are a way for the universe to know itself, a temporary arrangement of matter and energy that can look back at the cosmos and ask, what am I? Where did I come from? Where am I going? These are the deepest questions humans have ever asked. And the Milky Way, with its billions of stars and trillions of planets, with its black holes and nebulae, with its history and its future, gives us a framework for beginning to answer them. We are here, in this moment, in this galaxy, because 13.8 billion years ago, the universe began in the Big Bang. Because stars formed and died, enriching space with heavy elements. Because one particular cloud of gas and dust collapsed to form the sun and planets. Because, on one of those planets, life emerged, evolved, and eventually developed intelligence. Because countless ancestors survived, reproduced, and passed their genes down to us. Because of an unbroken chain of causation stretching back to the beginning of time, we are the universe's way of knowing itself. We are stardust contemplating stardust. We are organized complexity arising from cosmic simplicity. And for however long we exist, for however far we spread, we carry with us the story of the Milky Way, the story of our home. Thank you for joining us on this journey. Thank you for taking 2 hours out of your life to explore the galaxy with us. If you enjoyed this, if you learned something, if you felt even a fraction of the wonder that we feel when we contemplate the cosmos, then we've succeeded. This is Whispering Wonders of Science, reminding you that the universe is vast, mysterious, and beautiful. Keep looking up, keep asking questions, keep exploring, because the journey has only just begun. Until next time, fellow travelers, clear skies and safe journeys.